And then my final step will be to kill off the logs, to get rid of the logs. And to get rid of the logs, I take E on both sides. And that will kill off and get X, and then over here the log and E kill off, and I get 2 to the half power, which is just the square root of 2. And that's your solution. So if you take the square root of 2 to the square root of 2 to the square root of 2 forever, that's what 2 is. It's weird, right? Yeah. Curiously, I wonder, would this... So obviously, after I answer this, I asked him this. To the equals A, solve for X, right? Can you generalize this? Right, so what do you think? If it's 3, do you think it'll be square root of 3?
Yeah.
Yeah? It's not. It's cube root of 3. And then if it's 4, it's the 4th root of 4. And if it's 5, it's the 5th root of 5. And if it's A, it's the 8th root of A. Anyway, all right. I'm only bringing this up because I wanted you to see how that logarithm thing is very powerful. You can use that a lot of different places. All right, we're done with this section, all right? The homework assignment for that, I had you go through what, 40? What did I have you go through, like 45? So I would recommend that you do these, 51 through 60. Try them all. All right, we're moving on.
And this is the homework that on the thing says it was due to.
Yeah, we're behind. We're behind, which is, I'm not worried about the online stuff. Just keep up with the homework and just submit it as you finish it.
Yes, sir.
All right, we're moving on to the next section, which I thought a lot about not doing, but I'm going to do it. You could probably survive in Cal 2 without seeing this first, but I think it's worth us at least visiting. This is the section 3.5, inverse trigonometric functions. I'm not going to spend a ton of time on this, all right? I just want you to, because we could spend the rest of the day on this, and I don't want to. So I want to, it'll be on the test, for sure. What I want you to recall, this is something that I'm covering right now currently in my pre-cal class. We're talking about the inverse trigonometric functions. So in pre-cal, remember you have 6 trig functions, right? In pre-cal. You have y equals sine x, cosine x, tangent x, right? All these trig functions. Reciprocal of sine is cosecant, and then you have secant, and then you have cotangent, right? We have already established what the derivatives of all of those are, right? We know derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. I had a Cal 2 student who would have got 100 on their test last week, but wound up with, I think, an 81 because they missed one problem. And it was because they forgot, I don't know how they forgot, they were upset with themselves. They forgot that the derivative of tangent was secant squared. That was the one thing, and it messed up everything after that. So we know derivative of tangent is secant squared, right? Derivative of that, we know that we know a formula exists for it, right? We have it on our formula sheets. Those 3 we have memorized for sure. These 3 were, maybe we do, maybe we don't. But the main point is we know these derivatives, right? These are not open questions for us, right? We know these derivatives. Well, in pre-cal, after you discover and understand and graph these and try and understand their properties, after you understand those, then you start talking about the 6 inverse trig functions, right? And those are just the functions that undo these, right? So if you have the sine function, the inverse sine function undoes it. And whenever we did this in pre-cal, there was these domain restrictions. And again, I'm not going to go back and go through all the domain restrictions for these. I just want to remind you that when you have the inverse for the trigs, we had to restrict domains to have inverses. So the 6 inverse functions are the inverse of sine, which can be written this way, or it can be written arc sine x. Those were the 2 notations for the inverse sine function. Do they look, at least one of those look familiar to you? How many of you, this one is the one that looks familiar? How about this one? Yeah, no, okay, so I use this one almost exclusively, but this one is also used, so they're the same function. So we have one of them, right? Then we have the cosine inverse, and then we have the tangent inverse, right? And we got 3 more, right? All 6 of them. And the question now is, what are the derivatives of those, right? I mean, that seems like a natural question. So we would like to know what the derivatives of these are. And without us going into the detail of domain restrictions and all that stuff, just if I take this function, let's graph it. Let's use Desmos to graph it so we can all see what the inverse sine function looks like, because it's been a long time. I think for Desmos, if I type arc sine x, there we go. That's it. It's this little tiny function right here. That's it. That's because of all the domain restrictions. That's the graph right there. So I think it's obvious, hopefully to you, that that's going to have tangent lines, right? It's going to have slopes somewhere on that graph, and we want to be able to find the slopes, so we need the derivative. All right, to do that, I'm going to develop the formula for this. I'm going to show you where the derivative of this one comes from. And then the rest of them, I'm just going to give them to you. All right? So for the first one, we want to find y prime, right? And I'm given that y equals inverse sine of x. So I want to know what the derivative of arc sine is. And right now, I know nothing about this. Take derivative of that. I don't know what a derivative is. That's what I'm asking, right? So the only thing I do know is this. That because this is the inverse sine function, if I were to take the sine on both sides of this equation, that the sine is the inverse of the arc sine, right? These are inverse functions. So if I take sine on both sides, this right here, through the cancellation property, should just be x. So long as we're within the domain restrictions that we need to be in, we're not, again, getting into the details of that. This should be x, and this is sine y, right? So sine of y is x. If y is the inverse sine of x, then that means that sine of y is x. So from that, I'm going to get the derivative. I'm going to take that equation right there, and I'm going to take the derivative on both sides with respect to x. So I'm basically doing implicit differentiation. Right? I'm going to take derivative with respect to x on both sides. Carefully, what is the derivative of the left side? Carefully. What's the derivative sine of something? Cosine of it. Cosine of y. Good. Times dy dx. Chain rule, right? You have to take derivative of the y as well, right? So that's derivative of the left side. What's derivative of the right side? 1. D dx of x, that's just 1. And what are we trying to find here? Y prime, so dy dx, let's get it by itself. So how do you get dy dx by itself? Divide both sides by cosine y, right? So you get 1 over cosine y. And 1 divided by cosine is really what? Secant. So this is secant y. Do you all agree we have found the derivative? You agree? Yeah?
Yes.
But there's a problem. The problem is this function that I asked you to find the derivative of was a function of x, right? And so you would expect that our answer would have x's in it. And our answer has y in it. We really would like to have an answer that would be, like if I ask you for the derivative of x squared, you say 2x, right? You don't tell me something about y, you tell me something about x. So what I'd like to see is if I can get this expression, secant y, somehow turned back into something with x's in it. Yes?
Did you just replace the y with the inverse sine of x?
You could replace the y with inverse sine of x. You could. And then it would be an expression that has x's in it, right? Yes, we could. But I'm going to do something else, right? I want us to go back to this right here. That statement right there. And I'm going to do something with that statement that is extremely useful in Cal 2. From that statement, sine of y equals x. From that, I'm going to create what's called a reference triangle. I'm going to draw a triangle that represents that relationship. Let me draw it. It's a right triangle. I'm going to call the angle here y, because that angle, sine of an angle, right? Sine of an angle. So the angle's y. Sine, by definition, SOHCAHTOA, remember that SOHCAHTOA? Sine is which side of the triangle divided by which side? Opposite over hypotenuse. So I'm going to look at this x as being a fraction, x over 1, right? And now the opposite could be the numerator and the hypotenuse could be the denominator, right? So I can label this side what? X. And this side what? 1. Why in the hell am I doing this? Well, because I want to know what secant of y is, right? Secant of y. And if I draw this triangle, secant is the reciprocal of cosine. Cosine is the adjacent over the hypotenuse, right? So secant would be the hypotenuse over the adjacent. So if I just knew what this side was in terms of x, then I would have a formula, wouldn't I? So can we solve for this side? I'm going to call it a for adjacent. Can we solve for that? Yeah, a squared plus x squared is 1 squared. That's Pythagorean identity, right? And that means a squared equals 1 minus x squared. Move the x squared to the other side, and then take the square root on both sides. And we'll have plus or minus, but I'm only going to take the plus because it's the length of that side. So that's it right there, right? That's what the adjacent side is. So now, if I really want to come back over here and say, what's secant of y? That's cosine flipped over. Cosine is this over this, right? So secant is that over that. So my answer is 1 over the square root of 1 minus x squared.
For all the trig identities to get the answer like that with an x in it, you need to rectify?
For all, there's 6 inverse trig functions, right? I just showed you how to find the derivative of the first one, and I had to draw a reference triangle. For all the others, the 5 more, I would have to do the same thing. It would be a different triangle, but it would be the same procedure. Yeah? That's the derivative. So the derivative of inverse sine x is that. Yes?
Does that have any domain restrictions?
Negative 1 to 1?
Like if you were to, so like when I suggested that you replace the y, like I assume that that formula that we get would have a domain restriction.
What formula? Are you talking about this one?
So the one above that, when I suggested that, like, just to replace the y with inverse sine of x,
Yeah.
like I assume that that answer would have some form of domain restriction.
Yeah.
Does this answer also have a domain restriction?
Oh yeah, the domain restriction, see, look at the original function that we're trying to find the derivative of. That has a domain restriction. If you go back to pre-cal, you would see that the domain of that function is numbers between negative 1 and 1. You're only allowed to plug in numbers between negative 1 and 1 into this, right? So the derivative actually inherits that as its domain as well. But the domain of this is actually even more restrictive. Here I can include the 2 endpoints, 1 and negative 1. Here I cannot. I cannot plug 1 into this, right? I get division by 0. I can't plug negative 1 into this because I get division by 0. You can see it on this graph, okay? You can see it on this graph. This is the secant inverse, right? If I wanted to know the slope of the tangent line at 1, what would happen to the tangent line? It's going vertical. See? So the derivative should be undefined there. And then over here at negative 1, what's the slope over there? It's going vertical as well. And do you see that that formula breaks down at 1 and negative 1? Plug 1 into this, division by 0. Negative 1, division by 0. I don't know if this is answering your question. Okay. Yeah, we could spend, 2 hours talking about domain restrictions, go back in pre-cal. What's most important here is this method, right? If I'm trying to find the derivative of an inverse trig, like let's say this was cosine inverse. I would do cosine both sides it'd be cosine y is x. I would do implicit here, derivative of cosine y would be negative sine y dy dx equals 1. And then I'd solve, and then I'd draw my triangle based on a different relationship over here, right? It wouldn't be this, it would be cosine y is x. Draw your triangle. Yeah. All right, so I'm going to tell you these are on your formula sheets, but I'll write them on the board just so you have them. Just so I have them. I can say I showed it to you once. The derivative of sine inverse of x is 1 over the square root of 1 minus x squared. I just proved that to you, right? The derivative of cosine inverse of x is negative 1 over the square root of 1 minus x squared. It's almost the same exact thing, right? Except negative. And the last one, and probably the most important one, well, there's actually, what, 4 more? But I'll talk about the other 3 in a second. The derivative of arctangent x is just 1 over 1 plus x squared. That's it. There's no square roots. Just 1 over 1 plus x squared. This one right here, it comes up a lot in Cal 2. All 3 of those do, but the inverse tangent one comes up a lot. So I'm not proving those, right? And then there's 3 more, and I'll be honest, I don't even remember what they are, okay? But they're on your formula sheets. I could derive them. I could come up here and derive it for you, but those 3 are the ones that are most frequently used, and so those are the ones I want to show you. All right? Questions, comments, concerns? You have 3 new functions with 3 new derivatives, right? Which means product rule, quotient rule, chain rule, everything applies again, right? So I can now ask you this. If I give you y equals, let's go with secant inverse of the square root of x, and ask you to find y prime, you're going to now have the ability to use this formula, right? The derivative of inverse sine of something, right? Something is going to be 1 over the square root of 1 minus that something squared, right? So the derivative of this would be 1 over the square root of 1 minus the something squared. Am I done? What do I need still? Yeah, this chain rule, right? This is chain rule. I'm taking derivative of the arc sine of this. Now I need to take derivative of what's in there, which is 1 over 2 root x is the one I'll use, right? That's the derivative of what's inside. See? So we've just added 3 more functions we have to keep track of now, and all the rules apply again. That's a weird 2. Okay. 1 over 2 root x. There we go. And of course, you could square the square root under here and just make that 1 minus x and then be done. How about this one? How about what if y is equal to tangent inverse of natural log of x plus x? I want the derivative of this. So how do we take the derivative of arctangent of something? Arctangent of something? 1 over 1 plus that something squared, right? So this is going to be 1 over 1 plus what squared? All that stuff in there, right? All that squared. I don't care what that is. That's the first part of the derivative, right? Now, chain rule, take derivative of what's in there. What's derivative of what's in here? 1 over x plus 1. Do I need parentheses? Yes. It's chain rule, right? So it's this times that. You have to have both terms together. There we go. That would be it. Get the idea? We'll do one more. What about, how about e to the x cosine inverse of e to the x? Oh, that one looks fun. What's the derivative of this? What do y'all see? Product rule, good. Right there. That's a product. So we're going to do a product right there. And then when we're doing the product, we're going to have some chain, aren't we? So our derivative will be, okay, product rule. Derivative of the first one. What's the derivative of the e to the x? Itself, e to the x, times the second one with no derivative, right? Plus, now the derivative of cosine inverse of e to the x. Negative 1 over square root of 1 minus e to the x squared. So negative 1 over square root of 1 minus e to the x squared. Am I done there? Times what? That's the derivative of that, right? Derivative of that's e to the x times e to the x again, because you got to finish off the product rule. Okay? Everyone see that product rule there? Derivative of this times this plus derivative of this with that chain rule times the first one. If I put these two together, this could be written two different ways. You could write that as e to the x, that quantity squared, or you could write it e to the 2x. This is the one you'll most likely see in a book, because you're just multiplying x times 2 and getting 2x. It's the same thing. So you could put this e to the 2x on top up here, right? And that would just look a little cleaner, but we're done. Okay? So I would recommend that you, that's all I have to say about inverse trig functions, all right? There's homework problems here on your schedule. Where is it? You have a lot of stuff to do this weekend, I guess. Let me see, 1 through 6. No, okay, skip the 1 through 6. Don't worry about that. Those are just pre-cal problems. You can do them if you want. Those are pre-cal problems. 16 through 27. I would just start with the odds, maybe do 17 through 27. And then, you know, do the others if you're feeling lucky. All right? But you need to have some practice with those. Right? And that will be something I would ask, you know, I could ask on a test. I could now throw an inverse trig function somewhere in there. All right. We are going to start 3.7 now. I love this section. 3.7. Can y'all tell what it says there? What is that?
L'Hopital or something?
L'Hopital, yeah, L'Hopital. It looks like hospital. It's L'Hopital. Wait, I don't think that's spelled right. There's an S in there. Why don't I have an S in there? Yeah, I'm missing an S on the schedule. It's not Hospital. It's L-H-O-S-P-I-T-A-L-S. I don't know why. I've never noticed that's missing. It's spelt like hospital. Okay, 3.7. What's that?
How long has that been misspelled?
Years. Years. Yeah, I've never noticed that until now. It's pronounced L'Hopital. L'Hopital. L'Hopital's rule. The S is silent, yes. That's no excuse for me misspelling it, but. All right, L'Hopital's rule. So this rule is awesome, all right? This rule is awesome. What we're going to do right now is we're going to go back and talk about limits. And I know that we started the class with limits, right? And I know that when we did limits when we started, they were a little bit rough, and then we got past them, right? And we started talking about derivatives and stuff. We're going to go back and talk about limits again. But we're going to now have this new tool called L'Hopital's rule, all right? So recall from when we were first doing limits, recall this limit. Limit x goes to 0, sine x over x. Do I remember what that limit is? It's 1. And why is it 1? Do you remember why it's 1?
Why, but I remember
Sign's at, what sign is 0?
Well, sine of 0,
One at 0 is x.
sine of 0 is 0.
Oh, yeah.
0 divided by 0 is 0, right?
Yeah.
But you know the answer is 1,
Yeah.
but that's because I told you it's 1. This was that whole thing, sine junk over junk. Remember all that? And I said it's 1. I said if you want to know why it's 1, come into my office. I'll show you the proof. It's really actually pretty cool. But I also said later on, I'm going to give us a tool. We're going to be able to prove that that's 1 easily. All right? So right now, we know that this is 1. But it's just because I told you, right? So now let's figure out why this is 1 using L'Hopital's rule. So what does L'Hopital's rule say? Okay, what is the rule? So that rule says that if you're trying to take a limit, okay? If you're ever trying to take a limit and you have something approaching something, it doesn't even matter what it is. It could be x approaching 2, it could be t approaching infinity. It doesn't matter what the limit is going to, okay? But you have something on top and something on the bottom, right? So you have a numerator and denominator. And you're taking this limit and you're doing the direct substitution. Remember, direct substitution was always what we did first, just try and plug in the number and see what happens. If you do this, okay, so if you're taking a limit and you get 0 over 0 or positive or negative infinity over positive or negative infinity. Those for us in the past, whenever we've seen this 0 over 0 or any sort of infinity over infinity, in the past that has always been bad, right? We need to do some algebra, some trick, right? That's where we were. L'Hopital's rule says, no, you know what? If you ever have one of these two cases happen when you take a limit, then if the limit exists, because it may not, if the limit exists, if it does, it is equal to and you know what, just for the sake of making this easier to understand, we have some numerator and denominator, right? Let's say that this is some function f and some function g here, all right? So if we take a limit, we get 0 over 0 or infinity over infinity, then if the limit exists, it is equal to the limit, the same limit, but instead of having f over g, like we did before, what you can do is you can take the derivative of the top and the derivative of the bottom and then take your limit. So it's like if I'm taking a limit and I'm having trouble, right? I'm getting 0 over 0 or infinity over infinity. What I do instead is instead of doing f and g, I do the derivatives of these and then take that limit and see if it works. Yes? Not quotient rule. Yeah, it's not quotient rule. It's the only time ever that we're actually going to be allowed to take the derivative of the top and bottom separately.
Only if it's a limit.
Only when we're talking about a limit. Yeah, because this is not, notice we're not asking for the derivative of something, right? If I'm asking for a derivative of something, then I'm going to use quotient rule if I see a quotient. But this is asking for me to find the limit of something, and I'm getting infinity over infinity or 0 over 0. So let's go back to this problem right here. Take the limit right now, right? Take the limit. On the top, sine of 0 is 0, right? And then the bottom goes to 0. So we're all okay with the idea that this is 0 over 0, right? Okay? So I can now do this rule. So I need to somehow tell you I'm about to use L'Hopital's rule, right? I need to tell you. And different textbooks do it different ways. I need to tell you I'm using L'Hopital. A lot of textbooks will write an H on top of the equal sign to let you know that they're using L'Hopital's rule. Or they'll do an H and they'll circle it. Or they'll do an L, or they'll do an L and they'll circle it. I use an L and I circle it, and that tells you that I'm about to use L'Hopital's rule. So now what I'm going to do is rewrite the limit. X goes to 0, but now I can take the derivative of the top and bottom separately. So what's the derivative of the top? Cosine x. What's the derivative of the bottom? 1. Now try that limit. X goes to 0. Cosine of 0 is 1. And 1 over 1 is 1. And so your answer is 1. There you go. Now, I'm not going to prove this rule. I'm gonna have to go back, but I haven't thought about this in a while. I believe L'Hopital's rule, I think I'm wrong here. Hold on. I think I'm confusing this with something else. There was some rule where the person who's got the name for the rule actually didn't create the rule. They paid somebody to come up with some math, and they came up with something, and then they said, I'm going to claim it as mine. Yeah, there's some drama back in the day because, you'd have these very wealthy people, and they would be like hire people to like try and discover new formulas, new things like that. And it's like, okay, I'm going to pay you, you're going to work for me, but if you discover something, my name's going to be on it.
So I can be famous for being the nerd.
Yeah, exactly.
All right.
Yeah. Okay, so this is pretty good, yeah? Let's go back to a problem that you hated. One of them, I know there's a lot of them, but one of the problems that you didn't like. How about this one? Limit, let's go, x goes to 0. Remember something like this? Sine 5x over tangent 3x. And this was that one where you had to like rip it all apart and like say, oh, it'd be really nice if I had an x down there. So I'll just make an x appear. Oh, but I need a 3 as well, so I do 3 over 3 and slide it. Remember all that? It's been a while, but these kind of sucked, yeah? Well, let's just see what happens now. If we let x go to 0, 5 times 0 is 0, sine of 0 is 0. 3 times 0 is 0, tangent of 0 is 0. So here we get 0 over 0. Yeah? Okay, so I can apply L'Hopital's rule. Equals, by L'Hopital's rule, limit x goes to 0. All right, what's the derivative of sine of 5x? Cosine 5x times 5. Chain rule. You still have to do chain rule. If there's a chain up there, you got to do it. Over, all right, the bottom. What's derivative of tangent of 3x? Secant squared of 3x times 3, right? And now try it again. So if I try this, let me see. X goes to 0, cosine, 5 times 0 is 0, cosine of 0 is 1, and then 1 times 5 is 5, so my top is headed to 5, right? And then the bottom, let's see, secant of 0. That's the same as 1 over cosine of 0, right? 1 over cosine of 0. That's what secant of 0 is, right? Secant of 0 is 1 over cosine of 0, but cosine of 0 is 1. So 1 over 1 is 1. So this is all 1 squared, which is 1 times 3.